All right, this video is to introduce you to the first project for this course. And I think this is a pretty fun project because we'll be looking at real data from the MDOT traffic volume map in downtown Houghton and Hancock. So I have to use a system of equations to solve for some unknown traffic in Houghton and Hancock. So let's start reading this. For the three problems below, you'll need to use the MDOT traffic volume map. All right, let's click on that just to see what this is. All right, clicked on that. Hit OK here. And we'll be looking at 2022, so I'll just X that out. And let's zoom into Hancock and Houghton. And they have numbers on the roads. And if you click, say, right here, right, that's the road going west, the one-way road going west downtown Houghton. It says AADT for 2022 is 9,823. What does AADT mean? It means the annual average daily traffic. So what they do is they count the number of cars for the whole year of 2022, and they divide that number by 365. So you get like this average traffic for that year. So if you want to know the traffic for the whole year, you'd have to multiply this number by 365. That'll be the number of cars that traveled on that road in 2022. But we'll just be looking at the daily traffic for the first problem in the project. And so going from east to west, right, because this is a one-way road, there's 9,823 cars on average per day. We could look at the other roads, right? This is going from west to east here on the one-way. There's 10,046 cars on average per day. Now, if we go over here, this is actually a two-way road, right? So there's more traffic. We expect this since it's a two-way road. And it's 14,512 cars on that road on average per day. And what we're going to try to figure out is, for the first problem at least, how much traffic is going east on that road and how much traffic is going west, right? We don't actually know that because we're just told the total traffic, right, for that road. But we're going to try to figure out how much is going east and how much is going west by focusing on this intersection. Because over here, we do know how much traffic is going west and how much traffic is going east. And we'll use that information to help us solve for the east and west traffic on the two-way road. All right, let's go back to the project instructions. So zoom into downtown Houghton and click on the streets to find the annual average daily traffic for a road. That's the AADT. AADT is the total cars that drove on that road in a year and then divide by 365, like I was saying. Fill in boxes, the boxes on pages 2, 3, and 4. So we'll look at that in a moment. You may use a calculator computer to get from the augmented matrix to the reduced echelon form. Right, because some of these computations, if you're doing the row operations by hand, might be a little messy. It'd be good practice to do by hand, but you can also use a calculator, computer, and use the variable names shown in the picture below. So the x1, x2, x3, x4, all the way to x13 and x14. So use those names so we're all using the same language here with the names of our variables. All right, so there's a screenshot I took of the map we were just looking at, and I called them certain names. And we have this first intersection here. This is intersection A. Oh, it looks like I forgot to write A there, but this is intersection A. This is intersection B, commonly called the Yooper Loop. Okay, so kind of messy traffic intersection there. And then on the other side of the bridge that connects Houghton and Hancock, this is intersection C. So there's traffic going in and out of that in multiple spots. All right, so there's our screenshot of the map. Let's look at this. Now you can find X3, X4, X5, and X6 simply by just clicking on the roads on the map because they're one-way roads. So X3, X4, X5, and X6, right? Those are all one-way roads. The map will actually show that X4 and X5 has the same number. That makes sense, a one-way road. X3 and X6 shows slightly different numbers. That's because traffic, I guess they recorded perhaps two different spots and they did get a different number. That's because these smaller roads, you can have traffic entering and exiting. So there's a little difference there. All right. For node B and C, we'll be looking at the hourly traffic for B and C. X and X10 can be found with the 60 and 40% information described later. So we'll look at that too. All other road traffic is unknown because they are two-way roads. So all other traffic are two-way roads. So we're going to try to figure out how much traffic is going one way and the other way on those two-way roads. So we can find the solutions by setting up and reducing a system of equations. This is our application for the theory that we developed earlier. All right, let's look at the first problem here. We'll be looking at node A, the College Avenue split. Solve for the annual average daily traffic on eastbound and westbound College Avenue based on node A. That is solve for x1 and x2. All right, let's go back up to the map. Eventually we want to have our system of equations. We're going to write our augmented matrix in this box, and then reduce it and put it in that box, and write our final solution in the final box. And when you're working on this, you can put all your work on the left-hand side, and just put your final answers in these boxes. All right, let's go up to our map, and we're trying to solve for x1 and x2. We know what x3 and x4 is from our map, so let's go back to our map just to double check what those numbers were. So zoom in here. X3 is 9,823, and x4 is 10,046. I'm going to write that down on our page over here. All right, this is 9,823, and this one 10,046. All right. So the way you can set up your system of equations is, well, we know the traffic going in needs to be the traffic going out, right? Kind of like that previous homework that you looked at before. The traffic going in needs to balance the traffic going out, because if there was more traffic going in than out, then you'd have like a pile up happening. And if there was more traffic going out than in, then that would really make sense. It'd be like cars being created inside of the intersection. So the in needs to be equal to out. And the way we can write that for node A or intersection A, what we're calling the College Avenue split, is that x1 plus x3 needs to equal x2 plus x4. Right? The in needs to equal the out. Left side is in, the right side is the out for that equation. And we know what x4 and x3 are. So we have x1 plus 10,046 is equal to x2, which is unknown, plus 9,823. All right. And we can rearrange that to have, I'll write it over here, x1 minus x2 is equal to a known number. That would be 9,823 minus 10,046. So whatever that number will end up being, it'll be a negative number. So there's one equation, but there's two unknowns. We actually can get one more equation out of the intersection. Right, since x1 is the traffic going left and the x2 is traffic going right, the sum of those two traffics should give us the number that was given on the map. So the number on the map, right, was 14512, so 14,512. 14,512 needs to equal x1 plus x2, right? The sum of the left and right traffic needs to be the total traffic. So there's our two equations. That'd be our system of equations, right? And you can flip-flop the equations. You have this, the top equation really being the bottom one, or either way. Right? Order doesn't matter for which one's equation one, which one's equation two. But there's your system of equations that you would put here. And then the rest is the math that we've done before. You get your augmented matrix, get in reduced echelon form, and describe what the solution is in that final box. Okay, for node 2, or node B, the Euler loop is quite a bit more complicated. And actually, if we just go look at the map, x5 and x6 are known, right? We could click on the map to find those because they're one-way roads. But we only have, we have x9, x10, and 7 and 8. So we have 4 unknowns. and we'll only be able to extract two equations at this intersection. So we're not actually going to look at the daily traffic for this one. We're going to use the hourly traffic, because if we use the hourly traffic, we'll get more information about X9 and X10. So there's a little bit more information known about what happens from 8 to 9 a.m. So let's go look at that. Just remember X9 and X10 is the bridge traffic. Okay. So solve for the annual average hourly traffic from 8 to 9 a.m. on Memorial Drive based on node B. Okay, so Memorial Drive is the X7, X8 traffic. Okay, so we're trying to figure out X7, X8. It is known that from 8 to 9 a.m., traffic comprises 10% of the average annually daily traffic for all roads at node B. So in other words, if you're trying to figure out the hourly traffic for all the roads, just scale the daily traffic by 0.1, right? You might think, well, why aren't I scaling by 1 divided by 24? That's because the traffic isn't evenly distributed all throughout the day, right? It's actually, there's more traffic from 8 to 9 a.m. because people are going to work in the morning or going to class. So scale the daily traffic by 0.1 to get the hourly traffic. Right? But that still leaves us with 4 unknowns, so that doesn't help us solve things yet. That's just getting us situated for the hourly traffic instead of the daily traffic. This is where the extra information comes in. It's also known that from 8 to 9 a.m., the southbound traffic is roughly 60% of the bridge's hourly traffic. And the northbound bridge traffic is actually 40%. So there's 60% of the people going south on the bridge, and 40% of that bridge traffic is going north. Right? And this is real data. This came from one of the civil engineering professors that works with the bridge traffic, and so it's known that 60% is going south from 8 to 9 a.m. and 40% is going north. There's more people going south than north, so more people going to Houghton than Hancock in the morning. Might be because there's more jobs or something in Houghton, and also that Michigan Tech is in Houghton, so maybe more people are driving to Michigan Tech in the morning. So you can use that information to figure out the bridge traffic, X9, X10. So let's go back to our map. Let's go over to the bridge. Now the bridge, on average per day, has 25,768 cars on it per day. Now we want to get the hourly traffic, so we have to scale it by 0.1. That means we have roughly 2,576 cars, or you could round up 77 cars from 8 to 9 a.m. So that's how you get the hourly traffic. And then to figure out how much is going south, you'd scale that number by 0.6, 60%. To figure out how much is going north, you scale that number by 0.4 to get the 60% going south and 40% going north. So that's how you'd solve for the bridge traffic. And so you know those as numbers. If I go back to the project, let's say these are known now using that 60-40% information. X5 and X6 can be found by the map and scaling it by 0.1 to get the hourly traffic. Now you just have 2 unknowns, X7 and X8. You can do the same exact thing that you did to node A. Right? Get your 2 equations by, well, we know X7 plus X8 needs to equal the total traffic, which is 16,548. All right. And then you also need to balance the in traffic and the out traffic. So that would be where your second equation comes from. And then you have 2 equations and 2 unknowns. You can do the same thing, set up your system equations, reduce it, and eventually get your solution for X7, X8. All right, so that's for node B. Now, a common question at this point might be, what about all these smaller roads? Right, there is some maybe a little extra traffic going in and traffic going out. So, for example, maybe for going back to like node A, like some of this traffic might be going in and out around here. Well, just for the purpose of this project, let's say that that's negligible, partly because the in traffic, like the traffic entering on the one way and exiting the one way might kind of balance out, right? Because you can go down the hill and enter onto that road, and you can actually go back up and turn up the hill. So maybe that it roughly balances. And also, those are smaller roads, so the amount of traffic on the smaller roads is much less than the main one-way road there. So, and also that respect, it's insignificant. So the kind of the balancing out of entering and exiting from those smaller roads, and that they're just much smaller magnitudes, we're just going to ignore it for this project, right? To get an approximation to our solutions. Okay, and lastly, for node C, so I'll erase all this here. So for node C, we're going to do the same thing. We're just going to look at the hourly traffic. So we're going to be a little more specific. So we can use that 10% information and the 60-40% information so that we do know X9 and X10. But even when we look at the hourly traffic, these roads are both not one-way, but two-way. And so we have 4 unknowns once we know what X9 and X10 are. You still have 4 unknowns, and you'll be able to develop 3 equations for this intersection, right? One equation will be the usual in traffic needs to be the same as the out traffic. And then the other 2 equations comes from knowing what the total traffic is on the two-way roads, right? Because X11 plus X12, and when you click on the map, that'll be some total traffic. Next 13 plus X14 will be some total traffic for that two-way road. Right? So you get 3 equations, but you'll still have 4 unknowns. So that means you'll get an infinite number of solutions when you're working on intersection C. All right, so that's all my hints in helping you get started for this project. You can definitely let me know if you have any questions. All right, that's it for this video. Thank you.